We are presenting our work titled Teaching AI the Anatomy Behind the Scan, Addressing Anatomical Flaws in Medical Image Segmentation with Learnable Priors. This work was conducted by Hongfei Yang, Huazhu Fu, Mengling Feng, and I am Youngsuk Chun. One of the key features that distinguishes multi-organ medical image segmentation from standard natural image segmentation is the strong anatomical prior, such as the fixed number of organs, their shapes, and their spatial relationships to one another. For example, as shown in the figure on the left, the ground truth segmentation mask of the vertebra exhibits a consistent anatomical pattern in both shape and relative position. However, when we tested several commonly used segmentation models on these tasks, they often produced unrealistic artifacts that clearly violates anatomical rules. This indicates that the current segmentation models do not perceive or reason about organs in the same structured way that humans do. The figure on the right also presents additional failure cases from other tasks, such as prostate and fetal head segmentation, both of which rely on strong structural priors. Even small perturbations or noise in the input can cause the predicted masks to deviate drastically from their original shapes. These examples highlight that current models lack an understanding of anatomical consistency. They do not think about segmentation the way we do. In fact, this lack of awareness of structural priors may not be unique to medical imaging tasks, but can also be observed in natural image domains. For instance, the work by Juris demonstrated a substantial drop in model performance when images were edited to remove local textures, revealing the model's heavy reliance on texture cues rather than structural understanding. Similarly, in generative modeling, we often observe violations of basic structural rules. For example, generated images occasionally depict humans with an incorrect number of fingers or distorted body parts. So, we questioned ourselves how we could make segmentation models explicitly aware of anatomical priors, rather than simply hoping they would eventually learn such knowledge through longer training, larger data sets, or bigger models. Our solution is to incorporate anatomical priors directly into the model's input. Since the exact form of these prior is not known in advance, we design them to be learnable parameters. Given a generic anatomical prior, the model deforms it, guided by the input scan, to generate the patient-specific deformed priors. This deformed prior is then combined with the conventional pixel-level segmentation to produce the final segmentation map. Next, we discuss how the model performs deformation of the anatomical prior. The deformation process consists of two steps. 1. Learning the location mapping, where the model predicts a new spatial position for each point in the original prior. 2. Resampling the pixel values, where the anatomical prior is then resampled according to this newly proposed location to generate the deformed prior. The choice for the second step is relatively straightforward. We can simply use bi- or trilinear interpolation, which is both fast and differentiable. However, the first step, learning the location mapping, requires more careful consideration. Specifically, we must decide whether it is feasible to learn a dense location mapping for every pixel, or whether it is sufficient to learn a sparse set of mappings and infer the rest through interpolation. The location mapping in a 1D case can be represented as dots in 2D plot, where x-axis is the location before deformation and y-axis is after the deformation. The figures here illustrate two potential challenges in learning a location mapping for every pixel. First, the model size increases substantially as the number of estimated locations grow. Second, there is a lack of control over local coherence. Neighboring locations may not vary smoothly, leading to spatial discontinuities in the deformation field. While one could introduce regularization terms during training to enforce such smoothness, however, this approach often requires extensive hyperparameter tuning and adds additional complexity to the optimization process. Hence, we adopt an approach that learns the location mapping only for a subset of points and infers the remaining mappings using an appropriate interpolation algorithm. There are several possible algorithms for this inference problem. The figures here illustrate three potential approaches. Linear interpolation is computationally efficient, but lacks the expressiveness needed to model complex nonlinear deformation. Piecewise linear interpolation offers greater flexibility, but often produces undesirable sharp artifacts and can be challenging to implement. Finally, one could employ a neural net-based approach, which is highly expressive but introduces nested model optimization, making the training process significantly slower. Thus, we adopt thin plate spline (TPS) interpolation for this task. As originally intended, TPS requires only a small number of control points and infers the remaining location through smooth, continuous interpolation. The interpolation is achieved by computing a weighted sum of radial basis functions centered at each control point, as illustrated by the shaded bell curves in the left figure. Moreover, since the TPS formulation is linear in the parameters A and W, it has closed form solution. Returning to the 2D visualization of deformation, the figure on the left illustrates how TPS smoothly shifts all locations under the influence of only a few control points. As shown, the resulting mapping remains smooth and realistic, even with as few as 5 control points. Extending the TPS formulation from 1D to 2D is straightforward, and the entire process can be expressed compactly as a linear system. The figure presents an overview of AICNet. As mentioned earlier, the model takes both the input scan and the anatomical prior as inputs. The prior is deformed into a patient-specific prior using the deform block module. The resulting deformed prior is then injected during the decoding phase, guiding the network to produce an anatomically informed segmentation prediction. The figure in the center provides a detailed illustration of our deformation block. The deformation block performs a two-step deformation process. An initial coarse alignment using an affine transformation, followed by a more fine-grained deformation using TPS. You might wonder why we use a two-step process instead of relying solely on TPS. This will be clarified in the later slides. As shown in the top equation on the right, the affine transformation is responsible for learning only the translation parameters. AICNet is a cascaded network where the deformation and the prediction process is repeated at a local level to produce a more fine-grained and anatomically precise predictions. Our loss function consists of the standard soft-ice loss applied at both the global and local levels, along with our proposed centroid loss. The centroid loss is applied to the affine transformed prior to align its center with that of the ground truth. As illustrated in the figures on the right, without the centroid loss, the learned prior may produce multiple spine-like structures in the vertebra segmentation task. Incorporating the centroid loss effectively resolves this issue. This phenomena is closely related to the loss landscape of the soft ice function, and we invite the readers to refer to our paper for more detail. The figure on the left shows the learned anatomical priors for both the vertebra and multi-organ segmentation tasks. The learned priors appear realistic in terms of their size, shape, and spatial location, and they are successfully deformed to match each patient's anatomy. When our deformation module is integrated with commonly used segmentation models such as UNET or UNETR, we consistently observe performance improvements in both the dice score and Hausdorff distance. Here, we present some qualitative results that demonstrate the benefits of incorporating anatomical priors in the model's prediction. As shown, the predicted segmentations are noticeably cleaner with fewer artifacts and more anatomically consistent structures. Thank you for your attention, and please refer to our paper for more details.